For this project, I decided to talk about the concept of work. What is work, you may ask? Work is a transfer of energy. When a force causes an object to move, work is said to be done. The little boy in this picture, who is pushing the box, is an example of work being done. Understanding where work comes from. Work comes from forces. What are forces? Well, in the case of work, the force applied to work has to do with Newton's first law. The law states an object will continue to be at rest, and an object in motion will continue to be in motion unless acted upon by an external force. A force will change the state of an object. Forces can be better explained in free body diagrams. Here we have two free body diagrams, one of a box at rest and another with a box in motion. The one with the box at rest, you can see that there are two forces acting upon it. There's the force of gravity pulling it downwards and the normal force pulling it upwards. But when the box is in motion, you now have four forces acting upon it. You have the force applied, you have force of gravity, you have normal force, and you also have force of friction. Now that we understand work and we understand where it comes from, now it's time to speak of the equation. The equation is modeled as W is equal to Fa times delta D. In this table, I have shown what units each symbol is in and what the quantity of it is. So in the case of Fa, it's the magnitude of the force, which is measured in newtons. In the case of delta D, it's the magnitude of the displacement of how far it went, and that is measured in meters, and work overall is measured in joules. A unit analysis of it is the force times the displacement, which is equal to Newton times meters, gives you joules. Now to move on to a sample problem. A physics student is rearranging her room. She decides to move her desk across the room, a total distance of 3 meters. She moves the desk at a constant velocity by exerting a horizontal force of 2.0 times 10 to the 2 newtons. Calculate the amount of work the student did on her desk in moving it across the room. So first you want to put out what you know. We know that delta D is equal to 3.0 meters. We also know that the force applied is equal to 2.00 times 10 to the 2 newtons. We know that the equation for work is equal to W is equal to Fa times delta D, which in this case is equal to 2.00 times 10 to the 2 times 3.00 is equal to 6.00 times 10 to the 2, and we know that work is measured in joules. So then, therefore, the amount of work done by the student is 6.00 times 10 to the 2 joule. Now that we know the basics of work, let's get into a little bit more detail. I'm going to be talking about 3 scenarios when work is 0. The first scenario is when you're applying a force, but there's no movement being added. As you can see in my picture, the man is applying a great force to move the house, but the house isn't moving anywhere. That makes work 0. Mathematically, I've also shown this, that W is equal to Fa times delta D. But when W equals Fa times 0, work is then equal to 0. Another scenario where work is equal to 0 is uniform motion in absence of a force. My basketball was rolling on a frictionless surface. A force was used by my foot to get the ball to start rolling, but it continued to work on its own and move on its own. Therefore, in the equation W is equal to Fa times delta D, there's no Fa, but there is a delta D, but when you multiply that delta D times the 0 Fa, you get work is equal to 0. The third scenario is applying a force that is perpendicular to the motion. So in this picture, the little boy, he is carrying a book. Now, the forces acting on the book is Fa, but the force applied is in the upward motion. And yes, the little boy is moving, but the book itself isn't moving, making it that so that the book doesn't actually have a displacement. It just has an applied force. There's actually a fourth scenario when work is equal to 0. When a ball goes around in a circle, Ft is the force of work, which is equal to 0. The tangent makes a 90-degree angle with tension, making it cos 90, which is also equal to 0. Tension changes the direction of motion. But sadly, even though you may think you're exerting a lot of work as you're spinning said mass around in a circle, there is actually no work being done. Sometimes you're not always given the numbers straight up in a word problem to find work. Sometimes it's given to you in a graph and you need to know how to solve it, but don't stress or worry because you can still find work. To be able to find work, all you need to do is calculate the area underneath the graph. To calculate the area underneath the graph, you just need to know that length times width is equal to area. So in this case, the length of the graph is 10 and the width of the graph is 4. So you would just do 10 newtons times 4 meters gives you 40 joules. You can also take this and put it into your work formula of work is equal to Fa times d. Your Fa is equal to 10 and your distance is 4 meters, and you'll still get the same answer of work is equal to 40 joules. Work can also be done at an angle. When this is said to be done, the force and displacement are not parallel and pointing in the same direction, and you'll have theta, which is the angle between the force and displacement vectors. When this happens, you get a new equation for work. This equation will then be work is equal to Fa cos theta times d. Just like work can equal to 0, it can also be positive or negative. When work is positive, energy is being added to the system, so you'll have a positive answer for work. When work is negative, energy is being removed from the system caused by friction, and you'll have a negative answer for work. It can be broken down into this equation you see right here. Work times FFK, which is kinetic friction, is equal to kinetic friction times d times cos theta. When you rearrange, you figure out that theta is equal to 180 degrees, which leaves you with work equaling negative friction times d. Now to move on to another sample problem. Okay, how much work is done on an 8.00 kilogram wagon rolling down a flat sidewalk if a force of 60 Newton brings it to rest in 2 seconds? So in this case, we know that we need to use the formula work is equal to Fa times d cos theta. We know that since it's being pulled along on a flat surface, that theta is going to be equal to 180. We also know that Fa is equal to 60 newtons, 60.0 newtons. The thing we don't know is delta D. That is unknown. But what we do know is that to solve delta D, we need V1, V2, and time. We have time, which is equal to 2 seconds. We know what V2 is equal to, is 0, but V1 is unknown. To calculate V1, we need to solve for acceleration. We don't know that. So to solve for acceleration, we're going to use the formula F net is equal to Fa. Oh, and we also know mass is equal to 8.00 kilograms because F net breaks down to Ma, which is equal to Fa, which I'm going to make negative 60 because it's slowing down. And then to isolate A, you will have negative 60 over 8, which leaves you with A equaling 7.5 meters per second square. That is what acceleration becomes. So then we can change this here to 7.5 meters per second squared. So then since we have that, now we can solve for V1. So we're going to do acceleration is equal to V2 minus V1 all over t, which is equal to V2 is 0 minus V1 over t, which is 2 seconds, and acceleration is 7.5. So when you rearrange it, it becomes 15 is equal to V1. So 15 is your V1, so you can change that here. And since you know your V1 and now you know your V2, you can solve for delta D. So now delta D is equal to V1 plus V2 all over 2 times delta T, which equals 15 plus 0 over 2 times 2, which is equal to 15 meters is your delta D. And that's what you get left with. So then you can now sub in that your delta D is also 15 meters. Now you can go back to your work formula and do work is equal to FA times D cos 180, which is equal to 60 times 15 times cos 180, which is equivalent to negative 900.0 joules is your work. Therefore, the amount of work done is negative 900.0 joules. Lastly, I just want to talk about work's path dependency. Work done is path dependent when there's no friction, meaning friction dictates the path. But work done is path independent when there is no friction.